So in these next couple of videos, we're going to talk about circular motion, and I'm going to start off by defining a couple terms with an example. Okay, so we all know that Earth revolves around the sun. So here's the sun, right there, and there's Earth. Okay, so Earth revolves around the sun, and it takes, approximately 365 days for it to go all the way around. Okay. Earth also spins on its own axis, right? So there's an axis like right in the middle there, and Earth spins around itself, and that's what produces a day. Okay? So there's a difference between revolving around something and spinning on your own axis. So if you revolve about an object, that's basically turning about an external axis. So in this case, the sun is an external axis, and the Earth is revolving around it. In the case where Earth is revolving around its own axis, we call that a rotation. So its axis is internal to the Earth, and the Earth is spinning around its internal axis. Okay? So on the next page, I just have a couple quick definitions. We've got that a rotation is when an object turns about an internal axis, so in the case of the Earth revolving around its own axis to produce a day. And a revolution is when an object turns about an external axis, so that would be in the case of the Earth revolving around the sun. And then an axis is just a line about which a body turns. So I'm going to start the discussion of rotational speed with an example. Let's say that I've got this turntable. Let's say it's a merry-go-round. And let's say that I've got a horse at point A and another horse at point B. Okay. And let's say I'm going to ask you which horse is moving faster, A or B. Well, this depends on how you define speed. So I'm going to start by talking about rotational speed, which is also called angular speed, and that's defined as the number of revolutions per unit of time. So what that means is, let's say, the merry-go-round is revolving at 1 revolution per minute. So that means it takes 1 minute for this whole thing to go all the way around. Well, if that's true, and this is a rigid body, meaning that all the pieces revolve together, which they in fact do, A and B are traveling at the same rotational speed. It takes the same amount of time for A to go all the way around than it takes for B to go all the way around. So now let's consider the linear speed of horse A and horse B. Okay, well, we know that they have the same rotational speed. It takes the same amount of time for A to go around than it takes for B to go around, 1 minute, because we said it was 1 revolution per minute. However, A has to travel a much shorter distance than B. If you look at that, B kind of travels the whole length of the circle, while A travels a circle with a smaller radius. Around a circle with a smaller radius, that is. So B has a larger linear speed than A. Linear speed, also called tangential speed, is a distance moved per unit of time, while rotational speed is the number of revolutions per unit of time. So in the case of rotational speed, A and B both make the same number of revolutions in 1 minute. However, point B has to travel a lot further than point A during 1 revolution. So just to give you a quick formal definition, tangential speed, also known as linear speed, is distance moved along a circular path per unit of time. And angular speed, also known as rotational speed, is the number of revolutions per unit of time. So let's go back to the example to consider how these are related. Okay. So it's sort of intuitive that if rotational speed were to increase, linear speed will also increase as well. If I'm, making more revolutions per minute, I'm increasing my linear speed. I'm covering more distance per unit of time. So linear speed increases with rotational speed. And also, if I have points further out on this merry-go-round, let's say I had a point way out here, let's call it C, right? This tangential speed would be a lot larger than B's tangential speed as well as A's. So linear speed or tangential speed also increases as the radial distance increases. And what that means is the radial distance is the radius distance from the center to the point C or B or whatever. So this is radial distance R. Okay? So linear speed increases as rotational speed increases and as radial distance increases. So we can write this formula, put it on the bottom here, that tangential speed equals radial distance times rotational speed. So let's now try and go through a sort of more intuitive example. Okay, let's say I've got a circle with radius 5 meters, and let's say I have some particle A that's traveling around the circle, and let's say it makes 3 revolutions per minute. Okay, and I want to figure out its linear speed. Well, first I would want to figure out, okay, how far is it traveling? Because remember, linear speed is distance over time. So to figure out how far it's actually traveling, I need to consider distance around the circle. So distance around the circle is known as circumference. And just as a reminder, circumference is equal to 2 pi r, right? So the circumference of this circle is just 2 pi times 5, which is 10 pi. We know that this particle makes 3 revolutions in 1 minute. So that means it goes around the circle 3 times in 1 minute. So if it goes around it once, it travels 10 pi units. So if it goes around it 3 times, it's traveling 30 pi units. Okay? So in 1 minute, it travels 30 pi units in terms of linear speed. So speed is equal to 30, over minutes. So let me remind you of the formula that I wrote down a couple pages ago. We said that linear speed, I'm just going to call it V, is equal to radial distance, we'll call that R, times the rotational speed. Okay. If I had directly plugged into that formula, let's see what we would have gotten. So my radial distance is 5, that's just the radius. And my rotational speed was 3 RPM, 3 revolutions per minute. And that would have given me 15, which is definitely not equal to 30 pi. So that's wrong. So why is that wrong? Alright, well, let's consider some units. In order to plug into this formula involving rotational speed, the rotational speed must be in radians per minute or radians per second. Right now I have it in rotations per minute. Okay, so for those of you that don't know, there are 360 degrees in a circle, and 360 degrees is also equal to 2 pi radians. So there are 2 pi radians in 1 revolution per rev. And there's also 360 degrees in 1 revolution. So if I give you 3 revolutions per minute, I need to convert revolutions per minute to radians per minute, which I can do by multiplying by 2 pi radians per revolution. This is just a bit of dimensional analysis. You see that revolutions cancel, and I'm left with 6 pi radians per minute. Now this is a rotational speed that I can directly plug into that formula. Now let's see what would happen if I did that. So remember the formula was V is equal to radial distance R times rotational speed. And right now I'm going to just call rotational speed omega. Okay. So R was equal to, right here, 5 meters. Okay. And then the 6 pi radians per minute was equal to rotational speed. So I can plug that in. And I get 5 times 6 pi is 30 pi meters per min. And that's basically what I was looking for, right? We originally got that our answer was 30 pi radians per minute. Just for a quick note on units, we see that units don't totally work out here. I have meters and then radians per minute. A radian really means 2 pi radii, so in this case I have 6 pi radii, and my radii is 5. So essentially I'm just plugging that in and making that 5, and then 6 pi times 5 is 30 pi meters per minute. So to summarize, we know that tangential speed or linear speed is equal to radial distance times rotational speed. And that's often written as V is equal to R times omega, where R is the radial distance and omega is the rotational speed. I also want to emphasize that V in this case we're going to consider it as a scalar quantity. We're going to consider it as speed, just because in a circle, direction is always changing. Obviously, like when I'm here, I face a different direction than when I'm down here, and then when I'm over here. So just to keep things simple, we're going to consider tangential speed. Just speed, not velocity, for now at least. So in this video, we've learned that tangential speed is directly proportional to both radial distance and rotational speed. And that to be able to use this formula, rotational speed must be measured in radians per second, or radians per minute, and radial distance is normally given to you in meters. Alright, so in the next couple of videos, we're going to continue our discussion on circular motion and consider acceleration and centripetal forces.